So the last type of function that we're going to look at in this section is radical functions. And notice what I did here is they are radical functions. And if I was going to design a font that was called the rad font, that's what it would look like. So I used it because radical begins with rad.
Very cool, Mr.
Very
Hager.
cool. Yeah, huh? All right. Well, I got more coming up. You wait. All right. So, some examples of radical functions. Okay, radical functions either have a cube root, square root. They've got some kind of root in them. Okay, we haven't looked at graphing or solving any types of equations really like this yet, especially graphing. We haven't really done any graphing with radicals. So I want to talk about what some of the things are called there. Okay. Anytime that you write something that has a root symbol and then you put something underneath it, that is called a radical. This whole thing that I just circled is a radical. That radical has different parts to it. This number that's on the outside of the radical is called an index. And that index has to be a number bigger than 1, and it's always an integer. The index tells you the kind of root that you're working with, whether it's a square root, cube root, whatever. But that's what the index tells you. It tells you the kind of root that you're working with. The radicand, that's the part underneath the root. Could have variables, could have numbers, could have a mixture of both. But whatever is underneath the root symbol, that's the radicand. And then that symbol itself, I've been calling it the root symbol, the radical symbol, radical sign. That's just another name for the symbol. Okay, so the whole thing is called a radical or radical expression. The number on the outside, and smaller up at the top, is the index. And what's underneath is called the radicand. Any questions on those words? Okay. If you ever don't have an index, you always assume it's a 2. So when I write this, we're assuming the index on that is a 2. If you don't want it to be a 2, then you need to write down the number you want it to be. Now, instead of writing something as a root, you can write that as a number raised to a fraction. Does anybody remember what fraction you could raise 9 to? And it's the same as taking the square root. Yep. 1/2. Yep. Raising, let me fix that. Sorry, I got a little messed up. Okay, raising to the 1/2 power is exactly the same as taking a square root. What do you think would be the same as taking a cube root? Yeah? Right, to the 1/3 power. So the pattern is, if you want to change something from having a root to having an exponent, raise it to 1 over the index. Cube root, 1 over 3. Fifth root, 1 over 5. Raise it to 1 over the index. So how would I rewrite the 5th root of x to the 4th? Yeah, Charles?
X to the 4th power.
X to the what?
4/5 power.
Can you just break that down one step at a time for me? But yes, you are right.
Like, what do you mean?
Just getting rid of that 5th root and keeping everything else the same.
Oh, like 4 times 1/5? Is that what you mean?
So x to the 4th to the 1/5. Yeah. So that would break down as x to the 4th to the 1/5. And then when you have a power to a power, you multiply it. That's a reason why you might want to do this, because it lets you simplify your expression. And you can also work backwards from that if you had to. the x, if you look at this part right here, that's the power you're raising x to the fourth. And whatever number you're dividing by, that's the root. So you could take that and convert it back to what you started with as well. All right, so solving for what's called the principal root. The idea when we are solving for what's called a principal root, I want one answer. Roots always have as many answers as the index. So if you're doing a square root, there are 2 answers. If you're doing a cube root, there are 3. 4th root, 4. Not all the answers are real. Okay, we are only focusing on real answers in this section. But with the principal root, that means I want you to give me one answer. Just one. So if we're dealing with an odd root, okay, we're going to kind of break things down today into whether the index is even or odd. If we're dealing with an odd root, then we're going to be solving an equation that's like that. Let me show you an example. X cubed equals 64. If I wanted to get x by itself here, how would I get rid of raising to the 3rd power? Yeah, I would cube root it. I would cube root, and I would cube root. So I get x equals the cube root of 64. So now, to simplify that, all we have to do is just take the cube root of 64, which would be how much? What's the cube root? Yeah?
Is it 4?
It's 4. Yeah. So when you are solving a problem that has an odd root in it, if you don't have a nice number, you just type it in on the calculator, and we pretty much just write down the answer. Just take the cube root of each side. Now, when we're dealing with even roots, we got to be careful. How come the a, when we're dealing with an even root, has to be greater than or equal to 0? What if it wasn't? What would happen if this number was less than 0 when I try to solve that? Yeah?
You would have imaginary answers.
Right, I would have an imaginary answer. And when I'm asking for the principal root, I don't want an imaginary. I want a real answer. Right? So whenever we're dealing with principal roots, you'd never have a situation like this. You would have a situation more like this. To simplify something like that, you'd have to take the square root of both sides. Now, I've always said when you take the square root, it's always plus or minus. But if they specifically ask for the principal root, I want the answer that is not negative. So what would the principal root of 25 be? Yep, 5. That's the one that's not negative. So any question on what I'd be looking for if I want a single answer for an even root? Of course, if the radican's not a perfect square, you can always just type it in on the calculator and get the answer, but just don't write plus or minus unless it specifically says to. Okay. This one says principal root, so you don't do it. Yeah. All right, let's take a look at this. Okay, smaller or larger? And again, see what I get? It's smaller, larger is larger.
You had fun with the slideshow?
Yeah. All right, so the question is, when we take the square root of a number, does it get smaller or does it get larger? So let's try the square root of 4. When we take the square root of 4, what do we get? 2. So did it get smaller? Or did it get larger? Got smaller. Let's try square root of 18. Second, square root of 18, we got 4.24. Okay, what happened? Smaller. So it looks like when you take the square root, it gets smaller. Can anybody think of a number where the square root doesn't get smaller? Yep. 1. Square root of 1 is 1. Okay, so maybe then it either gets smaller or it stays the same. Well, let's try the square root of 0.5. Square root of 0.5. 0.71. What happened that time? It got larger. So when you take a square root, does it get smaller or larger? Well, it depends. Depends on what you take the square root of. Anything can happen. Smaller, larger, or stay the same. So let's look at that on a graph. And I want to kind of start to visualize square root even roots. So I'm going to draw 3 of them. I'm going to do square root of x. I'm pressing square root. All right. And now to do a 4th root, what you have to do is put in the index first, and then math option 5. Math option 5. Okay, to do the 6th root, put in the index first, math option 5. Okay, so I'm graphing a square root, a 4th root, and a 6th root. All right, let's do zoom 6. Now, first, just looking at those very generally, what do you notice about all of them? The blue one, the red one, and the black one. What do they all do? Yeah. They're all what?
All approaching probably infinity.
Yeah, the y value is approaching infinity on all of them. They all go up. And they also all go to the, which way? They all go to the right. None of them go to the left. And that's because we said with even roots, you cannot have a negative number under the radical symbol. Okay? Only 0 or higher. I want to zoom in because there's some interesting stuff going on near the origin that we can't see. So let's, now that we know it doesn't go negative, we don't need to look negative. And let's set our y max at, I think 3. Will probably give us a really good window. Okay, so there's my square root. There's my 4th root. And then my 6th root is going to be in black. So you've got blue, red, black. Okay, so let's look at that. First, does anybody see a coordinate that is common to all those roots? Yep. The origin, yep. That's because if you take the square root of 0, the 4th root of 0, or the 6th root of 0, the answer is 0 for all of them. Yep. 1, 1 is another point for the same reason. All of them go through the point 1, 1. Now, which root is the highest one? Which root is the one that's on top? Yeah?
X.
So the square root, the 4th root, or the 6th root?
The square root.
The square root is, so the blue one is always on top of the other ones.
Not always.
Not always.
The 6th root starts out on top.
Yeah, so the behavior of all the roots switches at that point. So let's start to write that down and see how we can describe that. So with even indices, the 2 points that we just found are common to all of them. We already had this zoomed out. What was the domain? We already kind of talked about it, but what's the domain for the radicand on an even root? Yeah?
0 to infinity.
0 to infinity. And what's the range? of all three of those graphs. Yeah?
Is it all the numbers?
So remember when we zoomed out, did the blue one keep going down? No. The blue, the red, and the black, they didn't keep going down forever. What was the lowest that they all went? Yeah?
0.
0. They didn't go any lower than 0. You can't tell in that picture, but the original one I had, you could. So when we are between, let's start with 0 and 1. So when you're in this section, right there, the square root is going to be the lowest, the fourth root is in the middle, and the sixth root is the highest. So in that section, it kind of follows the index. The bigger you make the index, the higher the root is above another one. So an eighth root would be even higher than a sixth root. The higher the index, the higher the root. Now, that behavior switches in this part. The higher you make the index, the lower it is on the graph. Sixth root is a higher index than a fourth root, so the sixth root is lower. So I'm just trying to point out the pattern of when the index indicates to you which one is on top of the other, and then when the index kind of tells you it's backwards. Okay. Any question on how we describe that here? Okay, so that's even roots. They start at a point and they curve. But that's the key. They start somewhere. Let's look at odd roots. Let's do a cube root and a fifth root. If you already have the roots typed in, you can just change the index. Just like that. Now, when we talk about cube roots, what's the cube root of, let's say, cube root of 8? Yeah, 2. How about the cube root of negative 8? What would you get, or what would happen when you do that one? Yeah?
Is that good?
Well, I times I is I cubed. That doesn't give me negative 2. I need something times something times something that gives me negative 2. I'm sorry, negative 8. Yeah.
Negative 2.
Yeah, I said negative 2. So the cube root of negative 8 is negative 2. So what does that tell you when you're doing odd roots about what you're trying to find an odd root of? Does it matter if it's positive or negative? No, you can do it either way. With even roots, no, you can't. But odd roots, you can do positive or negatives. And you will never get imaginary with odd roots.
How are you typing in like the fifth root? Like
What?
on
The fifth root,
yeah, I'm pressing that.
so you put in the 5 first,
Do I?
and then math, and then option 5.
Oh, okay.
Let's do zoom 6 on that so you can get kind of a zoomed out view. And you notice right away, it goes left and right. It does not go in just one direction. Odd roots go left and right. But there's a lot of interesting things happening that I kind of want to check out near the origin. So let's set our y max negative 2 to 2. Now, one thing you'll notice when we graph it, it gets pretty steep right in the middle of this curve. And whenever things start to get steep, the calculator kind of has a hard time. So it almost draws it like there's a gap. There's no gap. These are continuous. Okay. Let's look at that. And let's see if we can answer the same questions we did before. Are there any points on that graph that look like they're common to all of them. And this one's a little hard to see. I mean, I can try to like fix it. It should just continue in the middle right there. Yeah.
Would it be -1, 0, and 1?
-1, oh, you're negative at those three x values.
Yeah, yeah.
Yeah, so -1, 0, 0, 0, and 1, 0. Yep. And that kind of breaks your graph into 4 sections. So section 1 is here. That's 2. That's 3. And over here is 4. In what sections is the red one above the black one? Yeah. 4. Anywhere else?
I can't tell for 2 and 3.
It might be because I drew on it a little. I was trying to fix what it couldn't connect. Yeah.
2.
2. Yeah. 4 and 2. The red one is above the black one. And where is the black one above the red one? Yeah.
Sections 1 and 3.
1 and 3. So which root is on top here? It also depends on what section you're in. So when we did, let's just see which one was which. The red one was the cube root. The black one was the 5th root. So in sections 1 and 3, you can use common sense. The higher the index, the higher it'll be on the graph. The black one has an index of 5. The red one has an index of 3. 5 is above 3. But in sections 2 and 4, that's reversed. The higher you make your index, the lower it is on the graph. Okay? So roots have kind of some interesting things going on. Okay, so those points are common to all odd roots. Now, when I say that they're common, I mean if you don't shift it. If you take an odd root and you shift it up 3, well then there's still some common points, but they're all shifted. They're not these anymore. What about the domain and the range for odd roots? What does it look like the domain and range would be? Think about what kind of numbers did we say you could take an odd root of? Is it restricted like even roots are? Or is it something else? Yeah? Right. You can take an odd root of any number you want, and you'll get a real answer. What we're graphing here is principal roots. We're not graphing imaginaries. And it goes left and right forever. So the domain is all reals. How about the range? How high and low are those graphs going to go? Yeah? That's also all reals. So the domain and the range is all real numbers for odd roots. Now, let's see if we can describe what we had before. In the section that's less than -1, so I called that section 1, and between 0 and 1, I called that section 3. So in sections 1 or 3, the higher the root, the higher the index, the higher the graph is when you do it. Okay. Between -1 and 0, or greater than 1, that's sections 2 and 4. In those sections, it's backwards. The higher the index, the lower it looks on the graph. Okay, so I just want you to understand how different odd and even roots relate to each other as you change the index. That's all. Questions on that? Okay. So one other thing we always do when we graph functions is we do what to them? Instead of just keeping them the base function, a lot of times we take them and we,
Plug in numbers.
thinking of something graphical, we do to them. We did it with polynomials, we did it with rationals, and now we're going to do it with radicals. Yeah?
Factor?
No, something visual. It's more about a visual thing. So whenever we learn about a new type of equation, we always learn how to solve it. And we learn how to graph it and then do what to the graph? Yeah?
Transform it.
Transform it. So the transformations that we do are exactly the same as every transformations we've studied all year. When you have multiple transformations, you have to write them in a certain, excuse me, thank you, certain order. I'm not going to write down the A, B, C, and D because we've done it. We've already done it at least 2 or 3 times, okay, this year. But I'll say it just quickly. So the A is addition or subtraction inside the root. What does adding or subtracting inside the root do? What kind of transformation? Be the same as if you had something like this. If you were going to compare this to that, I want to know what the plus 2 does. It's inside the denominator. Yep. That is a horizontal shift. Yep. How about the B? That's multiplying by a number in front of x, but it's still inside the root. So what would the B do? Yeah. No, not a vertical stretch. Part of what you said is right, though. Yeah,
A horizontal stretch?
that's a horizontal stretch. Anything inside the function, whether it's inside the denominator, inside the root, whatever's inside the function you're studying, those are always your horizontals. Adding and subtracting is always a shift. Multiplying is always a stretch. How about C? It's multiplication like B, but it's on the outside. Yeah?
Vertical stretch.
That's your vertical stretch. And how about D? It's addition like A, but it's on the outside, not the inside. Yeah? Yeah. Right. That's a vertical shift. Okay. Vertical transformations, what you see is what you do. Positive value for D is up, negative is down. A number bigger than what for C would cause your graph to stretch bigger? You have to be bigger than 1. Yep. So if a C value is bigger than 1, you get a stretch. If you get a C value that's between 0 and 1, you get a compression. You could still say stretch by like a half. I know that means to compress. B. A and B are backwards. If you have a plus A, which way is your graph going to move? Yep, Charles?
To the left.
To the left. Minus A would move it to the, yeah,
Right.
to the right. If you have a value for B that is bigger than 1, like let's say B was 10, that's going to cause a compression by a factor of 10. Or you could say stretched by 1/10. Those are saying the same thing. I would just probably say horizontal stretch by 1/10 for that one. If I had this one, that's a small number in front of x. But smaller numbers make it bigger. So I would say this is a stretch by 3. Horizontal stretch by factor of 3. Okay, so you need to remember that the A and the B are backwards. What if the B was a negative? Let's see. What does that cause to do?
The reflection,
Reflection over which axis?
the x-axis.
So is B having to do with horizontal stuff or
Oh,
vertical
yeah.
stuff? Yeah, B has to do with horizontal. So B is a horizontal reflection. if it's negative. Horizontal reflection means you flip over the y-axis, you flip left to right. If C is negative, what kind of reflection would that be? Yeah,
Vertical reflection.
that's a vertical reflection. That means you're flipping up to down. That's vertical. That's over the x-axis. Yep. Okay, so hopefully, and we're going to study those same transformations again when we do exponentials next week. So when you start getting into exponentials, if you were comparing that one to that one, I would hope, even though we haven't studied them, that you could already figure out what the 1 and the 2 are doing. They're inside the exponent. So it's a horizontal shift and a horizontal stretch. Really, it's a compression. Horizontal stretch by 1/2, and it's a shift left 1. So transformations work the same all the time. That's what's kind of nice about it. Okay, how would I get g of x from the square root of x? What would be the only transformation I need to do? Yep.
A horizontal shift to the right 2 units.
So shift right 2 units. Yep. As long as you say which direction and how much, that's all you need. Shift right 2, perfect. How about this one? How would you get h of x? Yep.
Shift left 3.
Shift left 3. Perfect. Okay, you'd never have to compare something that's a square root to a cube root. That wouldn't make sense. You have to compare two roots that are in the same family. So square root to square root, cube root to cube root. Now, this one, we need to fix it first. That is not written in the standard format I showed up above. How would you fix this one? So it's more like what I wrote up above. Yeah.
Negative x plus 3.
Yeah, so let's think of it as the square root of negative x plus 3. Now we have two transformations, and they have to be in a certain order. So for that, look at the A, B, C, D in the chart that we went over. Start with the A, then go to the B. What's the first transformation that would happen there? Yes? Shift left 3. Perfect. And the second transformation. Yes?
Reflection across the y-axis.
Yep, you could say horizontal reflection, or even better, reflect over y-axis. Okay. Any question on describing the transformations? So now, when we do a transformation, what I call the center point for an odd root is going to move. Or if we're dealing with an even root, I call it the start point. Whatever type of root it is, an even root or an odd root, when you do a transformation, you need to find the new start or center point. And that's what we're going to look at now. So to find the new 0, 0 point, whether it's the start or the center, this is how you do it. It's going to be a coordinate. It's a location. So we have to find the new x and we have to find the new y. To find the new x value, set the radicand equal to 0 and solve it. Now, the reason you don't need to do anything else except the radicand for this step is because we're looking for the new x value. A and B are the only two things there that affect horizontal movement. C and D would be vertical stuff. C and D will have no effect on the x values. Okay? So we'll worry about C and D when we find the y. So just take what's under the radicand, or what's under the root, bx plus a, and set that equal to 0. Once you know the x value, you can plug it in and get the y back. Because you'll have a number you can fill in for x. Now that just gives you one point. It gives you the center point if it's an odd root, or the start point if it's even. You still need some more points. If I was doing an even root, would I check points on both sides of the new coordinate that I just found right there? Or would I check points on one side? If I was doing an even root, yeah?
One side.
One side. Okay. The graph for an even root does not go left and right. It only goes one way. You got to figure out which way it goes and then check a few more points like that. And you can make your sketch. And if you think, well, yeah, it just always goes to the right. Not if you flip it. You could have an even root that does this. Could go back the other way. All depends if there's a reflection. If you have an odd root, once you get the center, you're going to need a few points to the right. You're also going to need a few points to the left. You're going to need both. So odd roots are a little bit more work because you got to do both sides of the graph versus just one. So let's see if we can sketch this. Okay, regardless if it's the center or the start point, I don't even care about that right now. I just want to find that point. How do I get the x value for my new point that would have been at the origin before I transform it, and now it's not? How do I get that x value?
The radicand 0.
Set the radicand equal to 0. So we're going to get x equals, what is my new x value for this point? Yeah,
3 over 2.
3 over 2. Okay. Now I need the y value. Well, if you plug 3 over 2 in, what's 3 over 2 times 2? Yep. 3. And what's 3 minus 3? 0. It should be because that's the number we found when we set it equal to 0. So this better come out to 0 when you fill that number back in, or you did something wrong. Okay, so we got 0. What's the cube root of 0? 0 times 2? Still 0. Plus 1? 1. So really, that number right there is the y value. Because this whole part is always going to be a 0. So that is our new point. Is that a start point, or is that a center point, and we got to check on both sides? Which one is it? Start point or center point? Yeah.
Center point.
Why? Why? How do you know?
Because it's an odd index.
It's an odd index. This is a graph that goes left and right. So let's start to graph this. Just going to move that down a little bit. Okay, so the first point we can put right now is 1.5 comma 1. And how do you think I'm going to quickly get some more points? I want a quick way to get maybe 6 or 7 more points. Yeah.
Use the table.
Yeah, we're going to use the table. Do I need the table? No. I could plug these in by hand. It's going to take me longer though. And if I use the table, I know that there won't be any mistakes. So you're going to type in 2 times 3 math 5. So 2 times the cube root of 3 minus 2x. Make sure that +1 is out from under the root because it's a vertical shift. Okay. If we want, we can check, I actually have a table that we can use right here. We can check 1.51. Yep. So we found that one, right? And let's graph some of these other ones. Okay, 3, -1.8. So 3, -1.8. 5, -2.8. And let's go 9, about -4. That's pretty good. I can see the curve on the right. Let's do the left. 0, 3.8. 1, 2, about right there. -3, just above 5. 2, 4, 5, right about there. And let's just go -10, a little above 6.5. Okay, that's good. And now just do your sketch. Notice it doesn't look like the cube roots I was doing earlier. All these cube roots earlier looked like that. Why does that one have a different look to it? What in our problem caused it to look like that compared to looking like that? Yep. That's a reflection. Okay, that's a horizontal reflection. That's why it looks the way it does. Any question on that? Okay. I'm not going to go through and sketch all this one. I just want to ask a few questions about it. When we find that point that we do right away, would it be a start point or a center point? Yeah? Right. It's going to be a start point because that's an even index. Okay. When you find it, set that equal to 0. The x value is going to be 4/3, and I gave you a quick way to get the y value. What's the y value going to be for the start point? Yep.
-2.
Yes, -2. Now, because it's a start point, it's only going to go one way. We either need to check x values bigger than 4/3 or smaller, but it's only one way or the other. Let's try a value bigger. If you plug in 10, that's definitely bigger than 4/3. What's 3 times 10? And what's 4 take away 30? So now we have the 4th root of -26. Can we do that? No, we said earlier you got to have a positive number under here. So that means this graph does not curve to the right. You're going to have to plug in values 4/3 and smaller. Okay. Why does this root curve to the left? Most even roots go that way. Yep.
What's the reflection?
There's a reflection right there. It's not written in the correct order, but it's not written in standard order. But yeah, there's a reflection there. Yep. But this is actually a little easier because you only got to check points on one side. So I think once you get your start point, even if you just do 2 other ones, it's good enough. Okay, so last thing. Solving radical equations. The biggest thing we have to make sure we do when we are trying to solve a radical equation is you need the radical alone. It has to be by itself. And then, once it's by itself, like let's say you had this. To get rid of a radical, you have to raise each side to a power. It's up to you to figure out what the power is. The power is the index. So when we're dealing with a square root, what's the index? Yep, 2. So in this problem, you raise each side to the power of 2. And that's how you would solve it. We're not, you can write that, we're not gonna get into the sometimes twice part. That happens when you have two radicals in a problem, like this one. You have to get one radical alone, do the process, and then you have to do the process again. So it's kind of like raising to a power will get rid of one radical at a time. You can't get rid of two at the same time. But again, I'm not going to get into doing a problem like that. We don't have to worry about that. You do have to check for extraneous solutions. So you may find an answer that doesn't work. So plug it back in and check it. All right. So let's try. We're not going to do this first one here. We're going to do a different one. We'll start off with pretty straightforward. Square root of x plus 2 equals 6. First question, is the radical isolated on one side? Yeah, this is not isolated. That is. So now it says raise each power to the index. So square each side. Squaring and square rooting cancel. It's like raising something to the 1/2 to the second. If you raise to the 1/2 to the second, it's like now you're just raising to the first power because you multiply them together. So what do we end up with after we do that on each side?
X plus 3 equals 36.
X plus 2 equals...
X plus 2, I miscalculated that. And that's will be 36.
Yep. Very good. And when I solve for x, I get 34. And if you check it, 34 plus 2 is 36. And the square root of 36 is 6. Yeah. So that works. Okay. Let's try a little different one.
Is that 5 square root or 5th root?
That's 5 times the square root. 5 times the square root. Okay. Is the radical isolated here? No. Then we are not ready to square each side. We need to isolate it first. How do you isolate that root and get rid of the 5? Yep.
Would you divide both sides by 5?
By both sides by 5. Now we can square each side. We get 104. And if you check it, 104 minus 4 is 100. Square root of 100 is 10. 10 times 5 is 50. Questions on that? Okay. Now let's do this one. I think this is example 8, maybe. Okay. Is the root by itself on one side? What do you think? Yeah, Ash, what do you think?
Yes.
Yes. So what power would I raise each side to get rid of that root?
The
Third power. Cube root and cube cancel. And now I have that. What do you think I'm going to do with that now? And this is pretty much what we did in all of chapter 3. Yeah?
Subtract x to the 3rd.
Yeah, you can subtract the x to the 3rd, or you can add everything to the other side, but you got to get it equal to 0. Right? You got to find the roots of that equation now. So I don't know why I always like the highest exponent to be positive, so I'm going to put everything on the right. It makes no difference. I think that's because when I'm used to factoring, I always like the leading term to be a positive, even though I don't know if we're going to factor this. Well, actually, yeah, we are. We are going to factor. What kind of factoring am I going to do that comes up a lot when you have 4 terms? Yeah?
Group factor.
Yeah, I'm going to factor by grouping. What can you factor out of the first 2? that up. Sorry, when I move everything to the other side, it's minus x squared plus 2x minus 2. It hadn't messed us up yet, but it was about to. I just noticed it. Yep.
X squared.
Factor out the x squared. All right. What do the last two terms have in common? Yeah. The 2. So let's factor out the 2. Perfect. That's going to work for factor by grouping. What do both of those have in common? Yeah.
X minus 1.
Okay, so factor that out. That leaves me with an x squared and a plus 2. And now set each of those factors equal to 0 and solve. Okay. What happens when you set that first factor equal to 0? What do you get for an answer? Yeah. You get 1. I don't know if it works yet. I'll check it. What happens when you set the second factor equal to 0? Yeah.
Square root of 2 or square root of negative 2?
You get the square root of negative 2, which, tell me more.
I said it's an imaginary number.
Yeah, that's imaginary. Perfect. So we don't have to worry about that. It's going to be imaginary. Doesn't help us. All right. So now we just have to check if 1 works. Well, let's try it. 1 squared is how much? 1. 2 times 1? 2 plus 2. What's 1 minus 2? Negative 1 plus 2? 1. What's the cube root of 1? So we get 1. Now plug in the number we just found over here. What's 1 cubed? 1. So yeah, it works fine. So the answer to that one is 1. So once you get rid of the root on each side, then it's a matter of solving it by factor by grouping. You could use quadratic formula. I mean, if it got really bad, we could have had to use rational root theorem. But I would expect this to not get extremely difficult. So that's the homework. I do need to just adjust it. One question. So I'm going to skip 28. So the homework on 255 on the board. What I'll do is I'll put a list of test topics in the video while you guys are at lunch. That'll be posted hopefully within the next 20 minutes. And I will be after school for extra help.